Consider a function of two variables that's defined in a rectangular region in the xy plane, where x is in the interval from a to b, and y is in the closed interval from c to d. And if we subdivide this region using lines that are parallel to the coordinate axes, then the rectangles form a partition of R. So we can have many different types of partitions depending on how we subdivide the region. And if we index these rectangles using the index I, and we choose any small rectangle I, then this rectangle has a small area, delta A, with an index I. And that area is equal to delta xi, being the length of the horizontal dimension, while the length of the vertical dimension being delta yi. So recall our Riemann sum, where we subdivided a curve in one dimension using n rectangles. So for example, if we look at the xz plane, our area under the curve looks something like this, and we subdivided this region into arbitrary rectangles. So these have an arbitrary width, so they may look something like this. So for a function of one variable, we sum over the number of rectangles from index 1 to n, and we're summing the product of the function evaluated at some x coordinate multiplied by the width of rectangle I along the x-axis. So for example, this rectangle here has some width delta xi, and then multiplying this by the value of the function at some point along this rectangle, we got the left Riemann sum, right Riemann sum, and midpoint Riemann sum. So this point where the rectangle touches the curve can be chosen arbitrarily. So we can extend this Riemann sum to functions of two variables. So we have the sum over the number of rectangles in the xy plane, so from I equals 1 to n, and we're summing the product of the function evaluated at some point in each rectangle, which is an arbitrary point with coordinates xi and yi, and that's multiplied by the area of that small rectangle. So essentially, depending on the point we choose where the rectangular prism touches the surface, then the Riemann sums will be different. So for example, if we chose our rectangle like this, so this rectangular prism may touch the surface at an arbitrary point, or several points depending on the function and the size of the rectangle. And now if we take the limit of the Riemann sum, as the number of rectangles go to infinity, so as n goes to infinity, the area of the rectangle with the largest dimension goes to 0, and therefore so do the areas of the smaller rectangles. Then if this limit of an arbitrary Riemann sum exists, no matter what points we choose to evaluate the Riemann sum, then the limit approaches the same limiting value, and therefore the function f is said to be integrable, and this limit is the double integral of the function over the rectangular region, which we denote as a double integral of f of x and y over the area of the region. And similarly in Cartesian coordinates, we can use the notation of the double integral over the rectangular region of the function of two variables with respect to x and y. So a continuous function throughout the rectangular region is integrable, and note that discontinuous functions are also integrable, such as those with discontinuities on a finite number of points or smooth curves. So for example, recall that we can evaluate the integrals of functions with jump discontinuities piecewise. Suppose we have a positive function of two variables, which is defined over the rectangular region R in the function's domain, and we take an arbitrary rectangle in this region and form a rectangular prism with the surface, where the surface is defined as z is equal to f of x and y. And if we take the area of the base of this rectangular prism as delta A, and this is the area of a rectangle in this region, which we index as rectangle I, and multiplying this by the value of the function at some point in this rectangle with coordinates xi and yi, so this gives the z coordinate of a point on the surface. And if we sum these volumes over the number of rectangles in this region, then that gives our Riemann sum. Then this gives an approximation to the volume of the solid that's bounded below by the rectangular region R and above by the surface, defined by z is equal to f of x and y. So the solid region looks something like this. So to get the exact volume of this solid, then we take the limit of the Riemann sum as the number of rectangles approaches infinity. So in other words, the area of each rectangle goes to 0, and these rectangular prisms get thinner and thinner, so therefore smaller rectangular prisms are used to approximate the volume of the solid, and therefore this limit gives the volume of the given solid region, which is equal to the double integral of the function over the area of the rectangular region in the function's domain. Suppose we have a function of two variables, and this function is continuous throughout the rectangular region, where x is between a and b, and y is between c and d. Then Fubini's theorem states that the double integral of the function of x and y over the area of the rectangular region can be evaluated using iterated integrals. So in other words, we can first integrate with respect to x. So we're integrating the function from x equals a to x equals b along the x direction, and then we integrate the result from y equals c to y equals d along the y direction. So noting this inner integral is evaluated first, and the double integral can also be evaluated by first integrating with respect to y. So we integrate the function from y equals c to y equals d in the y direction, and then we integrate the result from x equals a to x equals b in the x direction. So this is valid for a continuous function. So as an example, suppose our function is equal to sine x on 4 plus sine y on 2 plus 2, which represents this portion of the surface above this rectangular region in the xy plane, where x is between minus pi on 2 and pi on 2, and y is between negative pi and pi. So if we apply the method of sections, we can effectively take a cross section that's parallel to the xz plane. So the area of the cross section is given by a at a particular value of y, and giving this cross section a thickness along the y direction, being an infinitesimal thickness dy, then we can integrate this from y equals negative pi to pi which gives the volume bounded by the rectangular region and the surface. So the z coordinate of every point on this surface in this rectangular region is given by this function. And recall that the area of the cross-section can be evaluated by integrating over x. So we break this cross-section up into infinitesimally thin rectangles with a thickness of dx along the x direction, and multiplying this infinitesimal thickness of the rectangle by the height of the rectangle, which is given by this function, and integrating this from x equals a to b. So in this case, we have x equals minus pi on 2 to pi on 2. So in this case, we're first integrating with respect to x while holding y fixed to evaluate the area of the cross-section that's perpendicular to the y-axis. And then this resulting area is then integrated with respect to y to obtain a volume of the entire solid. And now let's make a bit of room here. So combining these two results, we can write the volume as the integral of our function being sine x on 4 plus sine y on 2 plus 2 over x from x equals minus pi on 2 to pi on 2, and then we integrate the result over y from y equals minus pi to pi. So in this case, we're first evaluating the integral of our function with respect to x. So what we get is minus cosine x on 4 plus sine y on 2 multiplied by x. So note we're holding y fixed, plus 2x evaluated from x equals minus pi on 2 to pi on 2, and then we integrate this result from y equals negative pi to pi with respect to y. So here we see that cosine pi on 2 and cosine minus pi on 2 is going to evaluate to 0, so we can just ignore it. And then we get sine y on 2 multiplied by pi on 2, which gives pi by sine y on 4 plus 2 by pi on 2, which is pi. And then we have minus negative pi on 2, which is positive, by sine y on 2. So we just multiply this by 2. And then we have minus 2 pi on 2. So that gives 2 pi here. And then we integrate this result with respect to y. So what we get is minus pi by cosine y on 2 plus 2 pi y evaluated from y equals minus pi to y equals pi. So that gives minus pi on 2 by cosine pi, which is negative 1, plus 2 pi squared, and cosine negative pi is also negative 1, and negative is positive, and then subtracting the result we get minus pi on 2. And then we have minus 2 pi squared, and subtracting this gives 2 pi squared. So therefore, the volume below the surface is 4 pi squared. And according to Fubini's theorem, because the function is continuous over R, then we can change the order of integration and get the same result. So we can integrate first with respect to y, and then with respect to x. So in this case, we evaluate the inner integral from y equals minus pi to y equals pi, and then integrate the result with respect to x from minus pi on 2 to pi on 2. So I'll let you do that as an exercise. But visually, we're essentially taking our cross-section, in this case, perpendicular to the x-axis. So it looks something like this. And we're first integrating with respect to y. So we're getting the area under this curve for a fixed value of x, where the thickness of this rectangle is dy along the y direction. And then once we evaluate the area of the cross section by evaluating the interior integral for a fixed value of x, then we can give this cross section an infinitesimal thickness in the x direction, being dx, and then integrate this infinitesimally thin volume with respect to x to get the volume below this portion of the surface above the rectangular region R. So essentially the double integral of our function over the area of the rectangular region and these iterated integrals give the same value because they measure the same volume of the solid region bounded by the rectangular region in the xy plane and the surface defined by this function. Let's evaluate the following integral. So first we evaluate the inner integral with respect to x. So using u-substitution, we have u is equal to xy plus 1. So therefore du is equal to y dx. And therefore we can rewrite this integral as the integral of 1 on u over u. And for the limits of integration, when x is equal to 0, u is equal to 1. And when x is equal to 1, u is equal to y plus 1. So evaluating this gives the natural log of u evaluated at 1 and y plus 1, which evaluates to the natural log of y plus 1. And now we integrate the result with respect to y. So I have the natural log of y plus 1 integrated over y from y is equal to 0 and 1. So we can evaluate this using integration by parts. If we set u as the natural log of y plus 1, then du is 1 on y plus 1, dy, and dv is equal to dy, so v is equal to y. So we can rewrite this integral as u multiplied by v, which is y by the natural log of y plus 1, evaluated at y equals 0 and 1, and minus the integral of v du, which is y on y plus 1, integrated over y, from y equals 0 to 1. And now we can integrate by substitution. So if we set u equal to y plus 1, then du is equal to dy, and therefore we can rewrite this integral as the integral of u minus 1 on u with respect to u. And when y is 0, u is 1, and when y is equal to 1, u is equal to 2. So this is the same as the integral of 1 minus 1 on u. So this evaluates to u minus the natural log of u, evaluated at u equals 1 and u equals 2. So what we get is 1 plus the natural log of 2 minus 0 and minus 2 minus the natural log of 2 minus 1 minus the natural log of 1, which is 0. So what we get is 2 by the natural log of 2 minus 1. Let's evaluate this double integral over the given rectangular region. And if we recognize that it's easier to first integrate with respect to y, we can write our inner integral as the integral of xy by e to the xy squared with respect to y, evaluated from 0 to 1, and integrating the result over x from x equals 0 to x equals 1. And now if we apply u substitution, we say u is equal to xy squared, and therefore du with respect to y is equal to 2xy dy. So this inner integral becomes the integral of e to the u onto with respect to u. And when y is equal to 0, u is equal to 0. And when y is equal to 1, u is equal to x. So evaluating this integral, we get 1/2 of e to the u evaluated at u equals 0 and u equals x. So that gives 1/2 by e to the x minus e to the 0, which is 1. So we evaluated the inner integral, and now we integrate the result, being 1/2 by the integral of e to the x minus 1 with respect to x from x equals 0 to x equals 1. So what we get is 1/2 of e to the x minus x evaluated at x equals 0 and 1. So that gives 1/2 of e to the 1 minus 1 minus e to the 0, which is 1, minus negative 0. So what we get is 1/2 of e minus 2. Let's find the volume of the region bounded below by the given rectangle and above by the surface given by the following function. So what we do is integrate the function being y squared minus 4x squared plus 10 with respect to y or x, because the integral would be equally easy to evaluate. So we'll just integrate with respect to x from x equals 0 to 1, and then integrate the result with respect to y from y equals 0 to 2. So we're holding y fixed, so we get y squared x minus 4x cubed on 3 plus 10x evaluated at x equals 0 and 1, and then we integrate the result from y equals 0 to 2 with respect to y. So that gives the integral of y squared minus 4/3 plus 10 integrated over y from y equals 0 to 2. So integrating over y, we get y cubed on 3, and 10 is 30 on 3, so I have plus 26 on 3, y. Evaluated at y equals 0 and 2. So that gives 8 on 3, plus 52 on 3. So 8 plus 52 is 60 on 3, gives 20 units of volume.